So before we get into the specific notes, I do want to give you this kind of disclaimer about this last unit that we're in. This is the big unit. This is inferential statistics. This is what's going to be a good chunk of the test. And these first few chapters that we're talking about here, chapter 18, this is what we're doing now. It's not in any of the notes, but this is chapter 18. And this is really laying the groundwork. This is really just kind of basic level stuff before we do anything too specific. So chapter 18, chapter 19, chapter 20 are going to be things that are going to kind of repeat. Well, 19 and 20 are going to kind of repeat themselves as we go through this unit with some slight variations. So chapter 18, what we're doing here is going to be kind of laying some groundwork for what we're doing for the rest of the unit. And then as we proceed, we're going to cover things that are going to get recovered with different numbers and different parameters as we go. So once we go through it a couple of times, the basic structure is going to remain the same. So initially it might seem kind of slow, but then it's going to pick up because it's really, the process is really going to be the same. The underpinnings are going to be the same. So we're talking about these things called sampling distribution models. And what we're talking about here is we're going to simulate, as it says, flipping a coin 10 times and calculating the percentage of times it comes up heads and repeating this process 1,000 times. So just to be clear, we're for 1,000 times, we're flipping a coin 10 times and calculating the percentage of times it comes up heads. Obviously, I did not do this in person. I did this with the aid of a computer program, and the results are here. Now, as you'll see, we have percentages that obviously we're only going to get either 0 or 10% or 20% or 30% because we're only flipping it 10 times, and that's all we can get. So this is the result of all of these, of 1,000 samples of 10 and what their percentages of heads are. And as we can see, this has a mean of just a little over 50% with a standard deviation of 1.63, or 0.163. Not surprising, right? We're doing a coin toss. It's a 50-50 chance. Not surprising that our mean is around 50%. Now, again, with the aid of a computer program, we simulated flipping a coin 100 times, calculating out of that 100 the percentage of times it comes up heads, and repeating that 1,000 times again. So 1,000 samples of 100 coin tosses, and we kept track of the percentages. And the histograms below the screen, behind the screen here. And last time we saw it, it was kind of centered around 0.5. Well, look at that. We've got another model that's centered around 0.5. But look at the standard deviation. It's getting a lot smaller, isn't it? It's not nearly as big. I don't know why. I didn't mean to cross it off. I meant to underline it. Sorry. And as you can see, we're not going out as far. The graph is a little zoomed in, but you're not going out as far. You're not getting 10% and 90% like you did before. And if you go back one slide when we were talking about only flipping a coin 10 times, yeah, getting 2 heads or 8 heads isn't that uncommon. But when we start talking about flipping it 100 times, we're not getting 20, we're not getting 80, we're not getting 70, right? So as we flip that coin 100 times, it's still centered around what we would think it would be centered around, but it's getting less and less spread out. We're going to do one more, and we're going to flip a coin 1,000 times, calculate the percentage of times it comes up heads, and then repeat that process 1,000 times. You could probably know where this is going. It's still right in the neighborhood of 0.5. And that standard deviation just keeps getting smaller. And the spread of the data is less and less, because remember, we've got that thing called the law of large numbers. We haven't talked about that for a little bit, but that's that idea that the more you do something, the more it kind of the more the theoretical, the empirical, the actual probability works toward the theoretical, and that's what we're seeing here. The more we do it, we're getting less spread in the data, because, I mean, we're not even getting into 40 or 60%, because we're flipping it so many times. It's behaving just like we kind of think it would behave. Right? Most of the samples are close to 50%. So that's called a sampling distribution model, because what those three things, histograms that we just saw, shows the behavior of a particular statistic, in this case the proportion, of over all possible samples of size n. Obviously, we didn't see all samples. We saw 1,000 samples of size 10, of size 100, and a size 1,000. But what we're looking at is we're trying to get an idea as to how likely it is that a sample of a particular size will have a particular sample proportion. That's what we're going to be talking about here. We're still going to be talking in terms of probability, but we're talking about probability of a sample having a particular outcome, not one particular value being drawn from a population. There's a difference, right? So the histogram below, just to kind of bring back up here, shows, and the sample proportion is called p hat, and that's actually what it's called. That's the name of it. It's not something I made up. It's got that little caret symbol over the top of it. And so if we took many samples of 1,000 coin tosses and kept track of that, this is roughly what we would expect to see. And you can kind of see that, hey, that looks pretty darn normal. That looks pretty darn close to normal. Okay, well that must be handy. Given a reasonably large, a reasonably large n, the sampling distribution for sampling proportions can be modeled with the normal model with the given parameters. Okay? Now this is all in your formula sheet, so that's good. We don't have to necessarily memorize this, but it is important that we understand it. The mean of the sample proportions, the center of our histogram for all those sample proportions, is going to be just about the same, is going to be the same as the population proportion. So like we saw 3 different histograms of the p hat for coin tosses. They were all, regardless of the size of the sample, whether they were 10 or 100 or 1,000, they were all centered around what we knew to be the proportion of the times it's going to come up heads, which is, in this case, 0.5. The standard deviation can be found by taking p times q, dividing it by the sample size, which was either 10 or 100 or 1,000, and then taking the square root of that. And just as a reminder, p is our population proportion. Anytime we have just plain old p, it's the proportion for the population, as the p hat is the sample. Q is just the complement of p, that's because we've been using that right along, and n is our sample size. Meaning, and another way we can kind of put this, I don't know why I have the screen up so many times here. We can, when it's a reasonably large n, and we'll talk about that in just a second, we can model the sampling distribution for sample proportions with the normal model. And that normal model usually is described by the mean and the standard deviation. Well, okay, we're just dressing them up a little differently, but we're still talking about the mean, what we expect to get, where we expect the values to be, and then the standard deviation. They dress them up a little differently. Both of these are going to be in your formula sheet. Once we have those, once we're back together, we'll walk through that with the formula sheet. I highly recommend you have those all the time when you're doing these. Get comfortable using that, right? And these assumptions and conditions are ones that we need to speak to. They need to see those on the test. I need to see those. I don't want to see them written out. I don't want to see them named and then a check mark. That's not what we're looking for here. So assumptions and conditions, they need to be spoken to and met before you can use the normal model. And that's one of them is going to look very, very familiar because we were just talking about it. We've got a couple of assumptions, independent assumptions and the sample size assumption. This one here is, it has to be reasonable that the samples are all independent of one another, right? The outcomes of one sample shouldn't affect the outcomes of another. Usually it's hard to kind of prove that, but oftentimes if we know we have a random sample, that's usually good enough. And then the sample size n has to be large enough. Let's just further explain this. Say we're doing our coin toss, and we took samples of 2. Well, that really wouldn't be big enough, because here's why. Say we're graphing the outcomes. Well, there's only going to be 3 possible outcomes. It comes up 0, it comes up half the time, or if it comes up all the time. We're only going to have 3 possible towers. We need enough to have a good size histogram. Even though we're not going to be working with histograms, we're going to be working with the normal curve and z-scores and all that sort of thing. But we still kind of want to be thinking in terms of the histogram, in terms of we want that sample to be big enough, right? The next 3 are conditions, and we can check conditions. And a lot of times we're going to be given statements that can meet this randomization condition. Samples must be representative of the population they're drawn from. That's really important. And a lot of times in the problems, you're going to get the phrase a random sample. Or they're going to oftentimes indicate that it is randomly selected. That's good enough. That's all you can do for these types of problems. If they don't say that out specifically, you can also work around this one by saying, well, there's no reason to believe this isn't a representative sample. So when it says randomization, really we're looking for it to be representative of the population. The 10% condition. It can't be any big. It has to be less than 10% of the population. If it's that, it starts kind of affecting the independence of it all. So that's why we want to make sure that it has to be less than 10% of our population, and usually is. And the more practice we get on this, the more you'll say like, oh, I guess that really can be. It might not seem like it's less than 10% in a lot of problems, but they usually are, depending on how you look at it. And then lastly, but not leastly, the success failure condition. This is the one that we said when we were studying the binomial distribution. If we wanted to use the normal model to approximate the binomial, there it is. That was the one thing that we had to check. Now it's one of the things that we have to check, but we do still have to check it. I've found an acronym for this, IRS 10%. Right. Independent, random, success failure, and 10%. The sample size, to be honest, really isn't. It doesn't have to be that big of a sample to be usable. 10 is a big sample. 10 is a big enough sample. This one doesn't really come into play. I felt like I needed to because it was in the book, but really, if we can check IRS 10%, independent, random, success, failure, and 10%, we're in good shape. So what does this look like? So you got this problem here. Give it a second to, I'll give you a second to read it. Hit pause if you want. 22% of 18-year-old women in the United States have a BMI of 25 or more, considered to be associated with health risk, an increased health risk. So routine health check at a large college, right? The phys ed department usually requires students to come and be measured and weighed. They did a different system, asked for 200 randomly selected female students to report their heights and weights, and then calculated their BMIs. Only 31 of those students had BMIs greater than 25. All right, so our question is this proportion of BMI students unusually small? What we're really asking is getting 31 out of 200, if the population is truly 22%, how likely is that? All right, so we have to come up with a sampling distribution for this situation. So first, let's check our assumptions and conditions. Right? We'll kind of buzz through these because you don't have to write them down necessarily because they're here. Pause them if you do want to write them down. Random. We're told it's random, right? We're told it's randomly selected, so it should be independent and representative of the population. Done. We've checked independent and random with that one statement. Okay. 10%. And that's why it said a large college. 200 is more than likely less than 10% of the women in a large college. If they didn't say it was a large college, you could have said it's 200 is likely less than 10% of the women that could have been attending that college, because that's, I mean, it's going to be not unless we're talking about a college for a particular body type, which I don't necessarily think exists. It's a good representative sample, and it's not going to be violating that one. And then success, failure, yeah, you're going to want to do that each time, and there you have it. Okay. So we can use the normal model to describe the sampling distribution. Okay, we're not going to come up with the sampling distribution. We only have this data, but we have enough to work with. All right. So step 2, let's calculate the parameters. What are the parameters? What would we expect the BMI for this sample of 200 to be? Well, we would expect that the sample of 200 would have the same proportion as the population because it's a representative sample. Okay, so there's our mean. So our mean is the same as our population. We would expect this sample of 200 to be 22% 25 BMI or higher. Right? Standard deviation, we're just calculating, right? 0.029, we plug everything in, calculate it out, 0.029, and then we do want our p-hat as well. We want our p-hat as well. Our sample is 15.5%. We expected it to be 22%. Is this unusually low? That's what the question is. And we're asking about the sample. So would we expect a sample of 200 to have this as its sample proportion if it is coming from a population that is 22%? That's what we're trying to figure out. That's what we're trying to answer. We're trying to find the likelihood that we do that. Right? So now we just math, right? Now we're going to do some math. We still calculate the z-score just like we always have, right? We're using a normal model, so that's going to be a z-score. R value right? The 0.155 minus what we would expect divided by the standard deviation. That gives us a sample of z-score rather, of negative 2.24, right? So what we're really looking for is we're looking for the probability that the p-hat is 0.155 or lower, right? Which is the same as the probability that z is less than negative 2.24. We plug that into our normal CDF. It's still normal CDF, nothing fancy about that. And it's negative 10 comma negative 2.24. I might have this behind here. I didn't. And that would give us 1 1/4, right? So this sample, the sample proportion of high BMI students would occur only 1.25% of the time. So it is unusually small, right? If this truly is our proportion in the population, the likelihood that we would have gotten that sample proportion of 15.5% is really unlikely, right? So is this proportion of high BMI students unusually small? Yeah, it is. It is. What we're going to be working toward sooner than, pretty soon is, okay, so now what does that mean? What are we going to say as a result of that? Okay. Sorry this took a little bit longer, but this is an important idea. It does kind of come right back to this really straightforward idea of z-scores, right? But it's important to recognize that when we're dealing with samples, we are still looking for probabilities just like we have before with our z-score, but what we're finding the probability of is that a sample of a particular size would have a particular, in this case, sample proportion, or p-hat, right? We'll definitely be talking about this more when we're together again. Give the practice work a try, and please let me know if you have any questions. I hope this helped.